Welcome back. In today's video lecture, we will discuss about problems on the topics which we have discussed in the last week. In the last week, we have discussed about Faraday's laws of electromagnetic induction, and we have also seen how EMF is induced in the conductor because of magnetic fields. So, in today's lecture, we will determine the EMF based upon different scenarios. See, this is a simple problem where a conducting bar can slide freely over two conducting rails as shown in the figure. Calculate the induced voltage in the bar. So this is just like a train track where this is a train track. Okay. And this is just like a trolley or a train which can move freely in either direction. But in this case, they are taking it as origin and they are considering it as x-axis and they are considering it as y-axis. And they are saying that this is the track and this is your train or trolley. Or in this case, a conducting bar. Now this is able to move freely in this direction or in this direction. And this is the distance between the tracks, and this is the moment of the conducting bar. This is its velocity. U indicates a velocity, where B is the magnetic field which is present here. This dotted line, it represents a magnetic field which is present here. Okay, so they want to calculate the EMF which is induced in the conducting bar when it is placed in this magnetic field. See, this entire thing is magnetic fields. So they want to determine the EMF which is induced in this bar. We have seen in the last week that EMF can be induced in the conductor when there are three cases, right? EMF is induced in three cases. One, conductor is stationary, and B or H, whatever we call it, it is moving or varying with respect to time. Varying with respect to time or space. Second thing is conductor is moving and B or H or stationary, or what we call it as constant with respect to time. Case number 3, both or vary. Conductor is moving and B or H, whatever it is being given, they are also moving or varying with respect to time. In each of these three cases, you can experience an EMF induced in the conductor. So here in this problem, three different cases have been given. So we should determine the EMF in each of these cases. In the very first case, if you see, the bar is stationed at this position, whereas the B is varying with respect to time. It is dependent on time. So case 1. Case 2, bar is moving with velocity, whereas B is independent of time, and which means it is constant with respect to time. Case 2. The third one, bar is sliding with a velocity, which means it is moving physically, and B is also varying with respect to time. Case 3. So in each of these three cases, we are supposed to determine the EMF. Okay. So we'll start with the first case where we do have, I'll draw the figure again. Right, this is my bar and this is my field. The bar is presently here in this 0.08 meters. The set is 8 centimeters, so I'll take it as 0.08 meters. This is y direction and this is x direction. And the separation between them is 6 centimeters. I'll take it as 0.08 0.06 meters. Okay. So in this case, the EMF equation is given by EMF is equal to minus d dt by dt dot ds, and it is to be integrated over the entire surface, which you need to consider. So in this case, I am considering this surface where it is being spread from x is varied from 0.06, y is varying from 0.08. So when b is independent of x and y, it is dependent only on time. Okay. So first of all, let me calculate dv by dt. dv by dt is d by dt of b is 4 cos 10 to the power of 60 into 10 to the power of minus 3 milli is there. Az, right? This is a vector. Az. So if I do it with respect to time, cos becomes minus sign. So I'll get minus 4 sine. I'll get, and see, this is an internal derivation, so I'll get 10 to the power of 6 into 10 to the power of minus 3, and it is a vector in z direction. So this will become 10 to the power of 3, so which is nothing but 1000. So I'll write it as minus 4000 sine 10 to the power 60 Az. This is my dv by dt, isn't it? The next one I do need is surface. You know that surface, it is extending in x direction and also y direction. So I'll take Az bar, which is extending in dx and dy directions. With the x is varying from 0 to 0.06 meters and y is varying from 0 to 0.08 meters. So if I do the dot product here, dB by dt dot ds, this is dB by dt, which is minus 400 sine 10 to the power of 60 Az dot dx dy az. Right? When I do the dot product, see az dot az, it becomes 1. Right? So I'll eliminate this one. So my answer will be minus 400 sine 10 to the power of 60 dx dy. So this is what I'll write here. So if I want EMF, minus integral over the entire surface, it was minus 4000 sine 10 to the power of 10 to the power of 60 dx dy, isn't it? Yeah, this is 4000, right? Now minus into minus becomes plus, right? And dx and dy, we know the limits for this one. I'll take it as minus into minus, I'll take it as plus. So it is to be varied from y is equal to 0 to 0.08 and x is to be varied from 0 to 0.06 with 4000 sine 10 to the power of 60 dx dy. See, there is no term in terms of x and also into y. So I'll separate this one easily. So from x is equal to 0 to 0.06, there is no term, so I'll take it as dx into y term is also not there, so I'll separate it now. So here for integration of 1 I'll get x, for integration of 1 I'll get as here y. So I'll get it as 4000 sine 10 to the power of 60 into x, where x is varying from 0 to 0.06, into y, which is varying from 0 to 0.08. So here in this case it is 4000 sine to the power of t. This is 0.06 minus 0. I'll get as 0.06. This is 0.08. So I'll get 4000 into, it's a 24 it's 1. So this is 19.2 volts. This is the EMF for the case number 1. Okay. So for the case number 1, so what is the formula? EMF is equal to minus surface integral of dB by dt dot ds, where the conductor is stationary and the field is varying with respect to time. Thank you.